Hello friends, we are now going to start with actual circular motion. Now let us understand what are the different types of motion. The types of motion would be translational motion or rotational motion or oscillation. What is oscillation? When the particle moves to and fro from some mean position, it is called oscillatory motion. What is translational motion? In translational motion, the particle moves from one place to the other. Correct? I move from position A to position B here. So my coordinates or coordinates of the particle, they change. Correct? But then what about motion of a ceiling fan? The fan is moving, we say. Correct? But then does the fan change its position? No, it is right there in the ceiling. So 5 minutes back it was there, and even now it is there, and it is still moving. It is in motion, but then that kind of motion would be called rotational motion. Correct? So I have translation, rotation, and oscillation. Now this translational motion, we have seen different types of translational motion in our AS levels. Today we are going to start with circular motion, but then is circular motion a translational motion or rotational motion or oscillatory motion? We need to find out. Correct? Now when I consider the tip of the blade of a fan, correct? Tip of blade of fan. The fan as a whole, it is not moving anywhere. It is right there, right? 5 minutes back it was there, and now it is there, and after, let us say, another 1 hour, it is going to remain there. But we say it is moving. But then, if you consider this is, let us say, center of the fan, and tip of blade is this. It is moving like this. Correct? The tip of blade is moving along the circumference of that circle, and that motion is called circular motion. So whenever a particle moves along the circumference of a circle with some speed, it is said to perform circular motion. Now here most important thing is the distance of the particle from the center. It always remains same. Correct? The position of the particle with respect to the origin or with respect to the center of the circle remains same, but still it is moving. So and that is what we call circular motion. But when this particle moves along the circumference with constant speed or uniform speed, we call it uniform circular motion. Now when we say it is moving with uniform speed, what does it mean? We know that when a particle covers equal distances in equal intervals of time, we call it uniform speed. So that means, let us say in 1 second it moves from here to here, then in next 1 second it moves from here to here, in next 1 second it moves from here to here, and these distances, all these distances, x, x, x and x and so on. So if that happens, we say it is moving uniform speed. And when this particle moves along the circumference of our circle with uniform speed, we say it is performing uniform circular motion. Correct? Now I am going to change it a little here. Okay, I just complete this circle again, and instead of drawing those small squares there, I am going to draw a particle here at point A. Okay, and now I am going to draw a vector from center of the circle to that very position of that point or particle A. Okay. Now what is the distance between O and A? Obviously it is the radius of circle, so I call it R. Now I said I will draw a vector. So when I draw a vector, it has to have an arrowhead over here. Now when this particle from point A, suppose it moves to point B here, is the distance of the particle from the center going to change? The answer is no, obviously, because it is moving along the circumference of the circle. Correct. So this distance is all, again it is going to remain same, that is r. Correct. But this vector which was pointing towards east, now it is pointing somewhere else, right? Because the particle has moved. So now there has to be something to indicate the change, correct? Distance from the center is not changing, but this angle is changing, and that angle, we call that angle theta, and that angle, it is called angular displacement. It is indicated by theta. Alright, so now when I started, I said it is moving with uniform speed. Correct. So now as it is moving with uniform speed, my angle with respect to my initial angle, okay, it is always changing. Correct. So now see, in linear motion I have linear velocity, then linear displacement, correct? Linear displacement, linear velocity, linear acceleration. So likewise I should be having something here, correct? So if my angle, as the particle is moving from A to B to C to D and so on, if my angle changes, correct, that means my displacement is, angular displacement is changing. So if my angular displacement is changing with time, that means there is some angular velocity, correct? So I have angular velocity here. So if my angular displacement is changing with time, there is angular velocity. And like my angular displacement is denoted by a Greek alphabet theta, I am going to indicate this as omega, right? Omega, again it is a Greek alphabet. So now again, if my angular velocity is constant, then that means the particle is performing uniform circular motion. Correct. Now as I said, in linear motion, in translational motion, we had speed, we had displacement, we had velocity, and if my velocity changes with time, then we have acceleration. So do we have some type of acceleration here? Yes, we do have. Suppose my speed, the linear speed as it moves along the circle, circumference of the circle, if it changes, correct, that means my linear velocity is also changing. And if my linear velocity is changing, then my, then my angular velocity also will not be changing, right? So if my angular velocity is changing, that means there is angular acceleration, and we would denote that angular acceleration by Greek alphabet alpha. Correct. Now there is something very important that we would be discussing now. Alright, my particle is moving along the circumference of the circle of radius r with angular velocity omega. Correct. I have not said anything about whether this angular velocity omega is constant or it is changing, but for now let us consider it to be constant. And now, so that means this is uniform circular motion. Correct. So at any point of time, my linear velocity, magnitude of linear velocity would be v. Okay, now I'm going to call this v1 bar. Okay, at point B it is v2 bar. But you know what, this magnitude of v1 bar and v2 bar, they remain equal to v. And what is the reason? Because my speed is constant, right? My linear speed is constant. It is uniform circular motion. But then, there is one thing. When does a vector change? Either you change the magnitude or you change the direction, or both. Correct. So for a vector, if its magnitude is changing, I say the vector is changing. If its direction is changing, I say the vector is changing. If both are changing, then I say the vector is changing. So now here at point A, my velocity vector was pointing in this direction. At point B, it is pointing in that direction. Over here, it would point in this direction, because my direction of velocity is always going to be along the tangent to the circle. Correct. So that means my velocity vector is changing. But then if my velocity vector is changing, then there has to be some acceleration, right? So that means my uniform circular motion, though the linear speed of the particle remains constant, since the direction of velocity is changing at every point in the course of motion, my motion is accelerated motion. So motion is accelerated, that means there is acceleration, and if acceleration is there, then that must be caused because of some force, right? All these quantities, that some force and some acceleration we will be doing in the next video. Thank you so much.